So, welcome to the 5th lecture of combinatorics. Today we will discuss some elementary concepts. So, most of them you should know already from your 11th and 12th standard or from the first course you have selected in discrete done in discrete maths. So, but still we will quickly go through these concepts. In combinatorics, a few counting principles we can mention initially. One is called addition principle. So, if A and B are two disjoint finite sets, then the cardinality of A union B is equal to cardinality of A plus cardinality of B. For instance, I have a collection of see the numbers which are below 100, which are either which is each number in this collection is either an odd prime or an even number. How will you? So, these are disjoint set, is odd prime is never an even number. So, then I can see which are the odd primes below 100. So, that is 3, 5, 7 etc. So, we count first that set's cardinality we find, then we can find the cardinality of even numbers below 100, say like 2, say between 1 and 100, say 2, 4, 6, this number we can 15 numbers are there, we add them together. I mean, it's the simplest principle. So, when we have disjoint sets, and if I want to know how many elements are there in the union of them, we can just add the cardinalities of the individual sets. And the generalized addition principle says, okay, this is just for 2. So, what if we had several disjoint sets? Disjoint means pairwise disjoint. That means no two of them share anything, right? So, we can add the cardinalities separately. That is what the addition principle says. Nothing big. So, just to state that. Similarly, we can mention a subtraction principle. Let A be a finite set and B be a subset of A. Then the cardinality of A minus B equal to cardinality of A minus B. Here it is important to note that for this to apply this thing, we should have this condition: B is a subset of A. For instance, if A intersection, so if B had some elements which are not there in A, this would not have worked, right? For instance, you will be subtracting right more, right? So, for example, in our previous example, we were telling about numbers between 1 and 100. And suppose we are interested in odd numbers which are not prime between 1 and 100, then what will you do? We will consider all the odd numbers, say 1, 3, 5, 7, 9, 11, 13. This sequence of numbers, these numbers will form the set A here, right? And the prime numbers, see, we are only interested in odd prime numbers now. This we have to remove, like earlier 3, 7, because this is a subset of that. So, now therefore, to find the numbers which are odd but not prime, we can just do this thing, because that the other thing we want to, we are subtracting off the prime number which is a subset of this thing, right? It's also fairly simple thing. So, here is one question. So, though it looks simple, sometimes it can be useful, though it is not very difficult to come up with the answers. This intuitively we will use this principle, but still the questions can be more non-trivial than we imagine. So, find the number of positive integers below 1000 that have at least 2 different digits. So, let us say what is this question. So, I want the number of positive integers, I mean it's from 1, 2, 3, these are the positive integers below 1000, not including 1000, right, strictly less than 1000, up to 999, right. So, now you can consider this set A as this 1, 999, right. And then we can consider another set B, which is a subset of A, defined like this. B is what? The what was our question? The question was that have at least 2 different digits. I mean, if you take a number like 333, right, this is only one digit, or similarly just take 4, this is only one digit, right, one type of digit, one there is no 2 different digits here, right. Similarly, for instance, if I take the number 88, this is only one digit, namely one type of digit, right, 8 only, right, 8, both are 8, but 89 is okay because there are 2 different digits here, right. We want to count this kind of numbers. So rather than directly counting it, right, how do you go about counting this kind of it directly? For instance, 2 different digits, maybe the first digit can be filled in certain ways, second digit can be filled in certain other ways. We have to make sure that they don't repeat. So rather than directly doing like that, we can go in this way. First we consider this set A 1 to 99. B is a subset of A. What is that set B? We will consider the sets which have just 1 digits. For instance, these numbers 1, 2, 3 up to 9. This definitely doesn't belong to the kind of sets we want, right? So then we will consider these kind of numbers 11, 22 up to 99, and then we will consider 111 up to 999, right? So we can find A minus B here, right? So what we are asking for is the cardinality of A minus B, right? A minus B. So subtraction principle says this is A minus B. We know A here is 99 because 1 to 99 is the total number of numbers. Here B here is 3 into 9, 27, because first we have this one digit numbers 1, 2, 3 up to 9. Next we have this kind of numbers, this another 9 of them, and then we have this kind of numbers, another 9 of them, right? Sorry, another 9 of them. So another 9 of them. So these are the 27 one digit numbers. So that is our answer is this. How much is this? 2 and 7, 972, right? So this just to illustrate the subtraction principle. Then next question, next is the product principle. What do we mean by product principle? Let x and y be 2 finite sets, then the number of pairs x comma y satisfying x element of x and y element of y is the cardinality of x into cardinality of y. So actually, so here we have a set x, right? So this can be something, say a1, a2, an, right, n of them, and then y. So this can be say b1, bm, right? Clearly we are, what we are interested in is the cardinality of the Cartesian product, right? This is what is the Cartesian product, right? So the Cartesian product, we know these are things of the form xy, so that x belongs to A and y belongs to B, right? X cross y cardinality, right? So this is the, this is what we count, the cardinality of x cross y. So that is cardinality of x into cardinality of y. This we know. Cartesian product you might have studied in your 11th standard also, 11th and 12th standard also. So this is what we are counting. This kind of problems we see, the where do we need this kind of things. So we have seen an example of this thing earlier when we told that if you consider a complete bipartite graph with m vertices here, right, and n vertices on the other side. I remember you have to go back 2 classes before, and then we had considered this question when we studied the extremal graph theory question. So Manter had proved how many edges can we have in a graph without having a triangle. right. So, we showed that it's the number of complete bipartite graphs will give some an example where the number of edges possible are maximum without introducing a triangle, right. So, here let us say suppose there are m things here and n things here, how many edges can you have in this bipartite? Maximum, right. So, that this corresponds to x here, this corresponds to y here, an edge, see look, an edge correspond to an x comma y, where x belongs to the x this side and y belongs to y this side, okay. So, that is how number of edges possible are m into n, right. So, this we had done last time, and did we do any other, did we see any other example? Yeah, in another question we had seen this Sita, Geeta, Radha. These were the first names of some people, some collection of people. We told 13 people are there whose first names are always either Sita or Geeta or Radha, and then we told that their second names are either Rao, Ramana or Raju or Naidu, right. So, then these are second names always like this. Then we asked how many possible names can be formed in one of the earliest questions we considered, right, using this kind of first names and this kind of second names. This is our x here, this is our y here. A name that gets formed will be x comma y, Sita Rao, right, or it can be Sita Ramana or Sita Raju, Sita Naidu. Similarly, Radha Rao, Radha Ramana, Radha Raju, like that we can form. So, how many you can form? It is equal to cardinality of x into cardinality of y. Here it is 3 into 4, 12, right. So, this we had considered. So, we had already seen such things. This is quite intuitive. So, we are just formalizing the thing. So, that is all. So, now let us look at the so called generalized product principle. So, instead of just two sets, suppose we have k different sets x1, x2, xk, finite sets, right, and then the number of k tuples of the form x1, x2, xk satisfying so this xi comes from, so the ith component here comes from the ith set, right. So, this number is, you just multiply the cardinality of the sets together, this is what, right. So, this is the generalized product principle. So, we can consider a more interesting question about numbers to illustrate this point. For any positive integer k, the number of k digit positive integers is 9 into 10 raised to k minus 1. So, what do I mean here? So, you are interested in k digit positive integers, right. So, there are how many 1 digit positive integers? There are 9 of them, okay. 0 is not a positive integer. So, 1 to 9, right. So, 9 are there. How many 2 digit positive integers are there? So, it should be something like this, right, some x here, some y here. This x comes from, because 0 is not allowed here, x come from the set 1, 2 up to 9, 0 is not allowed as the first digit, right. Y comes from the set 0, 1, 2, 9. So, there are 9 choices for this and 10 choices for this. So, total x y can be, x comma y can be formed 9 into 10, 90 ways. So, 90 2 digit positive integers, which is, you can say, starting from 10 to 99, right. And now, if you want to talk about k digit, it is something like this, k digits, this position. So, this is x1, this is x2 and this is xk, right. This x1 can take values from 1 to 9 and this can take values from 0 to 9, this can take values from 0 to 9. So, here 9 possibilities are there for this thing. So, this, say we have x1 equal to, see the x1 equal to 9 here, because this first position can take values from 9 different possible values. So, this is x1 is this set, okay, 1 to 9, and similarly x2. where this small x2 can take values from, that has 10 possible values, and similarly xk has 10 possible values, namely 0 to 9, right. So, therefore, this is the number to 10, that is 9 into 10 raised to k minus 1. This is the thing. Okay. Next, how many 4-digit positive integers both start and end in even numbers? This is another question which we can. So, both start and end in even numbers, right. So, 4-digit, now we are talking about 4-digit positive numbers. Same, it will be 4 digits. The first position can take values from say x1. So, this x1 now 0 is not allowed here, 0 is not allowed, 1 possible values are 1, 2, no 4-digit positive integers, it should start with even number, right, start with even. So, that means so we cannot use 0, so it can be 2, 4, 6 or 8, right. There are 4 possible values here for this position. Now, the second position will get all the 10 possible values, namely x2. x2 is the set corresponding to the second position, that is 0 to 9, all the 10 possible values it can take, and x3 which correspond to the set of values which this third position can take, that is 0 to 9, right. So, 10 values here possible, and then this last position is again even, but now we can take 0 also, right. x4 is the possible values this last position can take, that is 0, 2, 4, 6, 8. There are 5 possible values. Now, the total number of possible values is 4 into 10 into 10 into 5, right. So, this is the way we can. So, they are the numbers which start and end at even numbers, right, 4-digit positive integers. So, here we are applying the product rule. So, what we are doing is for each position we are setting up a set, say xi, ith position correspond to the xi in the sense that is the set of numbers which can come in that position, right. And now we are counting the tuple x1 comma x, so say a1 comma a2 comma a3 comma a4 like, right, which ai corresponding to the digit that ith position will take, right. Then we know that then the cardinality is by multiplying these things together. That's all we are doing. Of course, these are all extremely easy intuitive things. So, but we just mention it. So, for the sake of completeness. Now, here is another question. Suppose that a password contains only digits from 0 to 9. Also, number of digits should be at least 4 and at most 7. How many passwords can be formed? Password, when I say password, it's something like a password which you use for ATM cards. So, only using numbers. So, that means you can use numbers 0, 1, 2 up to 9, right, and this is no more a positive integer or anything. So, you can start a password with 0, no problem. So, that means a 4-digit password you can form. You are not allowed to form 1-digit password because it's too easy to break probably. So, you can form a 2-digit password, 3-digit, sorry, you are not allowed to form a 2-digit password, you are not allowed to form a 3-digit password, you are allowed to form a 4-digit password, you are allowed to form 5-digit password, and then 6 or 7-digit passwords are also allowed, not more than that, because then the password may become too big, right. So, so how many such passwords can be made? Here, how do you do this thing? So, here this 4-digit password can be like this. This position can come from a set x1. So, how many possibilities? 9 possibilities, right, 0 to. Similarly, this can come from a set x2, this also has 9 possibilities, and this can come from a set x3, this also has 9 possibilities. This also can come from a set x4, this also has 9 possibilities. Sorry, not 9, so 10 possibilities, I am sorry, everything is 10 because 0 to 9 is 10, sorry, 10 possibilities. So, therefore, 10 raised to 4 possibilities for a 4-digit password. Similarly, a 5-digit password will have 10 raised to 5 possibilities because each position, there are 5 positions, each position can be filled in 10 ways each. So, similarly, the 6-digit passwords can be formed in 10 raised to 6 ways, and the 7-digit passwords can be formed in 10 raised to 7 ways. Here we are using addition principle. First we use the product principle to form these things, this 10 raised to 4, 10 raised to 5. How many 4-digit passwords are there? This is answered using the product principle. How many 5-digit passwords are there? So, this is answered using the product principle, generalized product principle we can say, right, because 5 times you are using that, and similarly these are all done, and finally we are adding them together because we know that a 4-digit password, the set of 4-digit passwords is disjoint from the set of 5-digit passwords and so on. So, we can add them up together. So, that is the yeah, that is what we can get, right. So, we are using addition principle as well as product principle there together. So, here is a more sophisticated question. Suppose that a password contains 5 digits, does not start with 0 and contains the digit 8, then how many possibilities are there? So, we are illustrating these principles, how these principles, product principle, subtraction principle, addition principle, how are they used separately or how are they used in together. I mean one apply one and then another and like that, right. So, in combination, right. So, this is what we are trying to see. Some examples, these examples are selected to illustrate that, like in the last problem we saw that addition principle and the product principle is used to count the number of passwords. Here this question says it contains 5 digits, a password containing 5 digits. How many are there? 10 raised to 5 are there, as you know, but then we also want to make sure that does not start with 0. So, then also we can count. So, that means the first position can be filled in 9 different ways, and the remaining 4 digit positions can be 4 positions can be filled in 10 ways. So, 9 into 10 into 10 into 10 into 10. So, that is the possible number of passwords, which 5-digit passwords which starts with 0. But then we also know that we also want to make sure that the password should contain digit 8. How many possibilities are there? So, this how will we do this thing? So, we when we know 8 digits, the digit 8 is present. So, we do not know where. It can be in the first position, it can be in the second position, it can be in the third position. So, we are talking about the 5-digit passwords, 5-digit passwords which does contain the digit 8, but does not start with 0, right. So, this is the 5 digits. Somewhere the 8 should come, that is the problem. We have to make sure that 8 is present somewhere. So, one way probably is to do that. Okay, suppose 8 comes here. Now, how many ways you can fill this thing? So, there are 10 ways of filling this thing, 10 ways of filling this thing, 10 ways of filling this thing. So, you multiply this out and you get a number, and then you say that here 8 comes. So, there are 10 ways of filling it, and then so same number, right. So, like that, can you add up all these things using addition principle and get the answer? So, here it is 8 into 10 raised to 4. So if I do it 5 times, 8 into 10 raised to 4, because assuming that 8 can be here, 8 can be here, 8 can be here, any of the places, right? So can I add them up together? No, this is not correct, because the addition principle can be applied only if these sets are disjoint. For instance, the set of passwords which have 8 in the first position, is it disjoint from the set of passwords which have 8 in the second position? Not necessarily. So there can be a password of the form 8 8 and something here, right? Say 6 5 4. This password has 8 in the first position, 8 in the second position also. So in both sets it comes. So therefore those sets are not disjoint. Therefore when you want to count the total number of passwords, we cannot add them up. So there are some intersections to minus off. So it becomes a little complicated. How do you do this thing? So we can deal with it using slightly more sophisticated techniques, but as of now, so we have a easier method, namely using the subtraction principle. So we will first note that the number of passwords. So if we don't have that 8 restriction, that means the digit 8 should be present. We just forget it. The number of passwords which does not start with 0. So that can be easily counted, because there are 9 ways of filling this. So there are the 10 ways of filling it, and 10 ways here, 10 ways here, and 10 ways, right? So it's 9 into 10 raised to 4. The only thing is to minus off those passwords which does not have any 8. I mean, you can subtract those passwords which does not start with 0 and does not have any 8. How that is easy to count. How? Because this is such passwords, say 5 digits. Here the first position can get anything other than 0 and 8. That means 8 possibilities here. Anything other than 0 and 8. That is 1, 2, 3, 4, 5, 6, 7, 9. Here but 9 possibilities. Out of the 10 possible digits, 0 to 9, we cannot give 8 here. Similarly, here also 9 possibilities. Here also 9 possibilities. Here also 9 possibilities. Now we can subtract these bad passwords. These are passwords which are having the first digit non-zero, but not having any 8 anywhere. Those passwords are not allowed, because we should have at least one 8. So this is the total number of passwords which were non-zero at the first digit, and and these passwords we counted here will definitely be a subset of that. Therefore we can apply subtraction principle. So that a minus b formula. So a minus b is what we want to find now, right? So we just minus it off, 8 into 9 raised to 4, and we will get an answer, right? So we just have to evaluate it and we will get the answer, right? It's a different way of doing it. So what we did is here we used the product principle and also the subtraction principle. It was like sometimes you may spend more time trying to work with the addition principle. We will see that we can't directly use it, and then we will have to do some more sophisticated things there. So rather subtraction principle was helping there. So though these principles are very simple, intuitive, still right in problems it can be helpful, for instance. So if we keep this in mind, there is another way of doing it, right? So that is that's why these principles are stated. Now find the number of positive integers. Okay, so this we have seen, and this we have. Keep digit positive integers. Yes, how many 4 digit positive integers? Yeah, this is the next one. For any positive integer n, so now we have studied 3 kind of counting principle, namely addition principle, second subtraction principle, then third product principle. So before going into the next thing, namely the division principle, we will just consider some very simple things which you already know, right? For a positive integer n, the number of ways to arrange all elements of the set 1 to n, right, in a line is n factorial. This you have already studied in your 11th and 12th standard. So this what we mean is, so for instance 1 2, right? So we can arrange it in 2 1 also. This is 2 factorial. 2 factorial is 2 into 1, right? Similarly, if you take 1 2 3, so this you can arrange in 1 3 this way is 1, it can be 1 2 3 1 3 2, it can be 2 1 3, it can be 2 3 1, it can be 3 1 2 3 2 1. So there are 6 possible ways of doing it, right? So this is actually 3 factorial, 3 into 2 into 1. So this is there are 6 possible ways of listing, ordering the elements of the set 1 2 3, right? So in principle, if you are given the set 1 to n, right, there are n factorial ways of doing that, because if you want to see this thing, so we just think of filling the positions. There are n positions. The first position can be filled in n ways. So any of these things can come there. So once if you give a number here, then the second number can be any of the remaining n minus 1 things. It can be whichever number goes here, we don't know which number, but after whichever is it, after that there are only n minus 1 possibilities here, right? Exactly n minus 1 possibilities. So after you give one number here, one number here, then 2 numbers will go from here, and there are n minus 2 possibilities here. And then after 3 numbers are gone from here, then we have n minus 3 possibilities to fill this thing here. And after 4 numbers goes from here, then n minus 4 possibilities to fill it here. So like that, finally you will have just one possibility here, right? This is this add up to n into, so n possibility here into n minus 1 into, so n minus 2 into, so into 1. So this is n factorial. That's what we just mentioned, right? And next notion we have to remember is that of a permutation. What do you mean by the permutation of a finite set S? It's a list of the elements of S containing each element of S exactly once, right? So like 1 to n. So you list it, but then you should not list like 1 2 1 3 4 3 like this, because you should not repeat things, right? So if you use 1, then you are not supposed to use it again. So you can say 1, then another 1, 3, then you should not use 3 again. So 4 2, this is okay, 5. This is a listing of 1 to 5, right, without repeating, but everything has come once, right, exactly once, right? The length of the list will always be n, right? So and every member of 1 to n will appear once. This such a list is called permutation. So how many permutations can be there? We have already seen that it's n factorial, right? Now the next notion is of making a partial list. Like there are n elements, out of that so k be a positive integer, so where k is at most n, then the number of ways to make a k element list from n without repeating any element, then the number of ways to make a k element list from n without repeating an element is n choose k, n into n minus, sorry, not n choose k, n it's called npk, right? And that's the old books have a different notation. So now the current, here I have written as nk. So the old books will also write npk. Sometimes I prefer to use this thing, so that because it reminds you that this is the permutation. So here what we are trying to do is we have n things like that, say 1 2 up to n, and we have to select k out of it. K is a smaller number than n, smaller or equal, and but it's a partial list in the sense that we don't need all the n things to be listed. Some k things to be listed from this thing, right? The property of the list is that you should not repeat elements, right? You have to take from this set, we should not repeat. For instance, you can 1 2 3 4 5, let's say n equal to 5, Now put k equal to 3. How many ways you can take? List it. For instance, I can start with 1, 1, 2, 3. Then I can start with 1, 3, 2, right? Then I can start with 1, 4, 5. Then 1, 5, 4. Then I can do 1, 2, 4, 1, 4, 2, right? So like that I can keep on going, or I can start with 2 and then 2, 1, 3, 2, 1, 4, 2, 1, 5, like this I can list, right? These are all possible ways of listing 3 things using this. From this 5 things, the list, in the list nothing repeats, just 3 things are taken from this thing without repetition. And how many ways you can do that? So it's easy to count, like we did earlier. The first position, there are k positions we have to fill. The first position can be filled in n ways. Any of these n things can come there. The second position can be filled in n minus 1 ways, because one thing is already allotted to this square, right? Only n minus 1 things are left. And the third position can be filled in n minus 2 ways, and so on. And the kth position can be filled in n minus k plus 1 ways, right? That's kth position, because this is n position n minus 0. This is n minus 1. The second position is n minus 1. The third position is n minus 2. That is n minus 3 plus 1. So the kth position will be n minus k plus 1, right? So this is the number of ways. So here our answer will be 5p3, also written as 5p53. So that is 5 into 4 into 3, right? Here n is 5, n minus 1, 4. So up to where we will go? N minus 3 plus 1, that is n minus 2. That is up to here. That is here 5 into 4 into 3. Note that we will have 3 terms here, right? Npk will have k terms. Start with n and k terms we count. That's what we do, right? That is this is this notation. Now let us say S and T be finite sets, and let D be a fixed positive integer. We say that a function f from T to S is D to 1 if for each element S element of S there exists exactly D elements T from T such that f of T equal to S. So what do we mean? So we are talking about something called a, a function from T to S. We are interested in some kind of type of function called D to 1 functions. D to 1 functions. So there are members of S and there are members of T. Now this goes somewhere. So for everything is mapped to something. A function means everything in this set will have an image here, right? And nothing here will have more than one image. This kind of, what is a function, what is a relation? You are supposed to review this thing in any of the elementary books. And now here, so like this, right? Now this is the point of view of the function from this side. So everything will have an image here, and nothing here will have more than one image. But from here you can have several pre-images, right? So now when I talk of a D to 1 function, so this is T, this is S. So starting looking from S, every member of S should get D pre-images here, pre-images. T things in T in this set should map to the same thing, exactly D things. Similarly for everything should be like that. So this is, I have taken D equal to 3 here, so like this. D equal to 3. Right. Now such a function is called D2 function. So here we have 1-to-1 functions when d equal to 1. That would mean that when you take t and s, there is a mapping like this, right. Everything here will have one pre-image. So everything will have only one image always, but what we are defining is based on what the members of S see, right, how many pre-images it has, right. If it is exactly one pre-image, then it is a 1-to-1 function. If it is exactly d pre-images, then it is a D2 function, like that. So now here is the division principle. Suppose there are two sets T and S such that we have this D2 function here, something like this, right, D2 functions here. And now if we count the cardinality of this, if we know this is S, say S is equal to some number k, then we also know how many here, how many are there in T. T will be equal to k into D, right, or k equal to T by D. This is what the division principle says. One will wonder what is so big about it. There is nothing big about it. So suppose for a party, several families attended a party, and then each family brought 2 children with them. So now if somebody wants to count the families, what probably they can do is to count the children, right, and say they found that there are 100 children, then they can immediately infer that there are 50 families, 100 by 2, because here T is the set of children, S is the set of families, S is the set of families, right, and then every family, so every child belongs to one family, but then from the family point of view there are 2 children associated to them, right. Children are mapping to families, but every family has 2 children associated with them. That is why this is a d equal to 2 case, right. So we can divide the cardinality of T by D to get the cardinality of S, right. Or if we know the family, the number of families, then we can get T by multiplying that. So this is the division principle. So we will just consider a simple problem to illustrate this principle. The number of different seating arrangements for n people around a circular table is n minus 1 factorial. So let us study this in detail. So here, so we have a circular table, say. So this is, so we want to arrange people around the circular table. How many seating arrangements are there? How many ways they can arrange? So for instance, this is first person 1, 2, this is one possible arrangement, 4, 5, 6, 7, 8, 9, 9 people are arranged like that. Now you see, if I had arranged the people so that this 1 is here, so this is here 1, 2 is the earlier one. Now instead of this thing, if I say 1 is here, and then 2 is here, 3 is here, 4 is here, 5 is here, and 6, 7, 8, 9. And this is not different from this thing, because just like the circular arrangement, it's just like the table is, this entire thing is rotated a little bit, that's all, right. This 1 came here, 2 came here, 3 came here, 4 came here, and so on, right. Nothing this is not a different configuration at all, right. Suppose I consider like that. Of course, one can insist that that's a different configuration. Suppose if I don't find any difference between them, it's in case it can be rotated and got the same position, right. So that way, so 1, 2, 3, 4, 5, 6, 7, 8, 9. This position won't be different from even this. So this position, for instance, if I write like this, so if I write something like starting from here 1 2 3 4 5 6 7 8 9. So it's by rotating one all the way here, right? That's how it happened. Now but on the other hand, we will consider that the reverse rotation, for instance, this suppose if I am writing 1 2 3 4 5 6 7 8 9, sorry, for instance this one 1 2 3 4 5 6 7 8 9, this is considered different. This is our choice. In fact, it's one may wonder why do you think like when I rotated to the clockwise direction it was considered same, but when I rotated not rotate means when I flipped it, right? So this also in some sense is similar, but there are some subtle differences here. For instance, if I look that who is my, if my criteria of deciding which is whether something is same or not was by looking at my left neighbor. Always if so I can define that two configurations are same if my left neighbor, the left neighbor of everyone is same. Here it is like that. For instance, the left neighbor means the neighbor. So for instance, if I am standing here, so this is my left neighbor, right? So left neighbor, or maybe the neighbor in the clockwise sense, right? Clockwise sense is always same. So this whichever way I rotate in this direction, so it doesn't matter. So my right neighbor will remain same for everyone. But here it is not like that. Earlier 2 was my clockwise neighbor, so right and left, that's a little confusing. Let's say clockwise and anti-clockwise neighbor. So the earlier the anti-clockwise neighbor was 2, now it is clockwise neighbor was 2, now it's anti-clockwise neighbor, right? So there is a difference here in some sense, right? So therefore we are defining that two seating arrangements are same if for everyone sitting the clockwise neighbor remains same. Clockwise neighbor remains same. The positioning doesn't matter. So that's how we define this thing. Then how many different arrangements are there? This is the question. One way to attack this thing is to note that. So for instance, like we can try to set up a function, T21 function from T to S here. Then what is T? So suppose we give numbers to the chairs, right? In the seating arrangement, we give, say this is chair number 1, this is chair number 2, chair number 9. Then every time we shift a person, the arrangement will look different, because on the chair number 1 who sits, it's different this time. Then earlier the person number 1 was sitting on chair number 1, now the person number 1 has gone and sat in chair number 2. Though it was just a rotation, still we can think that it's different. So but then if you are numbered, this chairs are numbered, then it doesn't matter whether we make them sit in a circular way or straight line, right? Because it's the first chair, second chair, that's all we mean, right? 9 chair. So this comes back to our permutation problem. If there are n chairs, that is n factorial possible ways, right? Now let's say all these n factorial possible ways are placed in T. Now the question is, if the chair numbers were not there, so one of the seating arrangements, right, would have corresponded to how many of these listings? This is the question. So for instance, this was 1 2 3 9, right? So here this would have gone to in the listing, this would correspond to 1 2 3 9, but then when I rotate it, so this 1 came here, 2 came here, 3 came here. So now this will be another, so when I read out the number of chairs, though without chair numbers this is same, but if the chair number was there, we could have written it like 9 1 2 3 up to 8, right? Similarly, when one more rotation is done, so the 8 will come here, right? 8 9 1 2 3 7, like that. Then we have 7 8 9 up to 6. So like that we can rotate it 9 times here, right. So if there are n people, sorry, right, n times we can rotate it. We can start with 1, so we can start with 9, we can start with 8, we can start with finally 2 also, right. 2, 3, 4, like finally 9, and 1 will come here. So this 1 will go all the way first here, second here, third here, like that, finally it will come here, right. But when the chair numbers are not there, all these things corresponds to the same seating arrangement. We can't distinguish between them because the clockwise numbers always clockwise neighbors always remain same in any of the seating arrangements. Just that this look different only because we assigned certain numbers to the chairs, and when they moved we noticed that actually the person who is sitting in this particular chair number is different now. But the chair, once the chair number is deleted, we can't even identify which was the arrangement, right. So therefore so this we can see as T as the number of arrangements with chair numbers, that means the linear arrangements, and this S as the kind of configurations we want to count when the rotations doesn't matter, right. After rotating we still say that is the same configuration. So that means one configuration here will correspond to exactly n different configurations here. Here this will be n and so on, right, n and so on, right. So d equal to n here, right. So we should also notice that this whatever this gives, and this is this the things which will arise, linear arrangements will arise from a different configuration will be totally different, right. We after all to make it we have to, so here if by rotating 1, 2, 3, 4, 9 and say by rotating 1, 3, 2, 4, this will be always different because the clockwise neighbor is different here. So there also it will be different. So there at least for one of the members it was different here. So in the linear arrangement also it will reflect, right, the clockwise the guy who is next there. So therefore they will all be different. So therefore we can see that this here we have a function which is n to 1 from this to this. That means each member of S is seeing n pre-images. So the cardinality of T we know now already. That was easier for us to count. That was n factorial. We already know it. And then D equal to n. Then that means this is n fact. So that means n factorial by n. That will become n minus 1 factorial. This will be the size of this S. That means the configurations we want to count, namely the configurations where the rotations does not make a difference. That means the configurations where we say that two configurations are same when everyone seated has the same clockwise neighbors, right. Those will be n minus 1 factorial. This was an application of the division principle. Right. The next question we want to consider is, so this, let n be a positive integer and k less than or equal to n be a non-negative integer, then the number of all k element subset of n is n into n minus 1 into up to n minus k plus 1 by k factorial. So this is, so here finally we are coming to the question of counting the number of k subsets of k element subsets of an n element set 1 to n. How many are there? The notation to denote this number is n, this like this, n c k. Remember the other one was n k here. This is n c k. So the so we have old notation was n p k. So here we have n c k, right. Now what is this thing? So we are talking about how many ways, how many subsets, k element subsets we can take from n. That there is a difference here. For instance, the earlier example of 1, 2, 3, 5 for n equal to 5. So when we listed down the number of possible ways of making 3 lists without repetitions, right. So that was, we counted 1, 2, 3, then we saw 1, 3, 2, then we told 1, 4, 3, 1, 3, 4, all these things were allowed. But then this 1, 3, 2 and 1, 2, 3 will be only one subset, that is 1, 3, 2. There is no difference between these two configurations when we are thinking of subsets, right. 3 element subsets only 1, 3, 2 here, right. This 2 will not be there. So even actually from this thing we can get 6 different configurations in when we count this number, right. For instance, it can be 1, 2, 3, 1, 3, 2, it can be 2, 3, 2, 2, 3, 1, 2, 1, 3, or it can be 3, 2, 1, 3, 1, 2. 6 different possibilities are there, but here it's only one possibilities. That is the main difference here. So this is the number of possible subsets. Here also, to do this thing, we will show that this number is actually n into n minus 1 into n minus k plus 1 divided by k factorial, right. Here also again we will use the division principle. How do? We will set up a set T, we will set up a set S, and then here this T will correspond to the number nk, namely all lists of k things taken from n things without repetition, right, but their orders matters, right. This many will be there. And now here the is the actual things we want to count, namely the subsets. Now we ask one subset, how many of these things correspond to it. Okay, so if you give me 1, 2, 3 as a subset, I know that this can give rise to 6 different things here, right. That's what we were telling, right. 6 different things here, right. So similarly, so if it is a k subset, k factorial different things. So this I will explain in the next class more carefully. Thank you.